So we're screening sensors around about doors and things and thinking about doing this. And Andy comes along and says, well, what you need is an efficient protocol to be able to send this data around. We discussed the whole issue of separating data and control and thinking about safety critical systems and so on. So he introduced us to the idea of MQTT.
Today we welcome Professor Jeremy Graham Frey, Professor of Physical Chemistry at the University of Southampton. As far back as 2006, his laboratory was using MQTT and Java-based mobile applications to monitor critical systems related to lasers and other equipment necessary for his students to perform their research effectively and safely. One of the pivotal moments was the introduction to MQTT by Andy Stanford Clark, which revolutionized how they sent and recorded data from their experiments. This episode is a deep dive into the synergy between human ingenuity and machine efficiency, offering valuable takeaways for technologists, researchers, and anyone interested in the future of scientific exploration. This is our first episode of this podcast, and I think that's a really interesting coincidence with the fact that you were really the first documented use case of MQTT that I could find when I was, really rummaging through the Internet Archive to figure out like who was there at the beginning. And of course, having talked to Andy and Arlen, I know there was some work going on at some of the oil companies and things like that. But you were really public about it. So I'm kind of wondering, like, if you were to take yourself all the way back to like the very early days of that, what even led to you using MQTT? Like, what happened?
I think this is taking us back to the early 2000s, way back there. And we were very lucky that clients had, literally just by accident, actually, that the UK research councils were going to fund an effort on what it came called in the UK eScience. It was called Cyber Science in the US and various other names around the world. But it was basically to fund the program in using computers to aid research. Now, some of that was big computation, and there was a lot that went on that. And some was all the other things that went with how can we actually use modern computation, use modern programming, use information systems to make sure that we could do research more efficiently and more productively and extend the range of research. And we bid in to do this in terms of a grant that was actually called CombiChem. It was sort of a combination of combinatorial chemistry that was around at the time, high throughput chemistry, and all the necessary data computational infrastructures that were needed to deal with this. Because we weren't expected to be one of the routes that would get funded, but in the end, we were one of the few people proposing to engage with what you might call the end users. The majority of the program was really like middleware. In fact, the success of the program is that nobody remembers it because it's all gone into the middleware. It's all there. It's all being used, a lot of it. But we've got involved at the more user end. And that user end, we did look at how you ran experiments, how you could automate experiments, how you could design experiments, the sort of software needs to design them, how you could collect the data. Electronic laboratory notebooks, we were one of the early groups looking at from a research perspective, but there've been other standards on that. How they would ensure that the data has got quality metadata associated in it, improve reproducibility, reduce uncertainty, all the topics that actually for the last 20 years continue to be discussed.
Yeah, exactly.
So you might think they don't get anywhere, but hopefully we did. But as a result of that, we linked up. As part of that project now, we were working with our X-ray crystallographers. There's still one branch of chemistry that is ahead in terms of reproducibility and data standards. I'm also came with it. I was a parent and still in IUPAC, the International Union of Pure and Applied Chemistry, and that's where many of the chemistry international standards are kind of agreed and set. So I come from that perspective too. And had been working with some computer scientists in Southampton who were experts in the semantic web. These were the very early days of the semantic web. Relatively early days of the web when you consider what we used to do then compared to what we can do now. And we set up the various interactions, and the program that was set up, which we were then part, facilitated linking with industry. And linking with industry, conveniently, our local industry is IBM Pursley. And so we were put in touch with a number of players there who were very interested in working with us, experts on image processing, experts on databases, experts, as it turned out, on communication protocols. And that's where we met great Andy Arthur Clarke, who was a great, as you will appreciate, tinkerer with things as well as a master inventor. And when we were talking about, what do you do now? You do experiments. What do we want to do? We want to make sure we do experiments properly. Probably is, well, you design them well, and you look at the results at the end, and you work out, well, what worked, what didn't work, what can we improve? How are the results of one day different from results of another day? Well, now that means keeping a good record, but it also means keeping a good record of all the things that are happening. That at that point, at least you might expect to influence the experiment. It's always a circular process here because you learn more as you're doing it. And I was working at the time on experiments that looked at chemistry at the air-water interface. And we used to bounce slides. I won't go into the details at this stage of the experiments, but we had a relatively high power nanospectral lasers, which were reasonably state-of-the-art at the time. And imagine if you've got a dish with liquid in it, then it bounces around and people jump around in the rooms. Now people open the doors, close the doors, making sure that people didn't walk in unexpectedly finding a laser on, which is dangerous. Are they wearing the right equipment? Recording the temperatures. I mean, we actually had some new labs built at the time into an old building. And you would have thought we might have had access to the building management system to know the temperature of the room. No, that's not allowed. That's not possible. So we're stringing sensors around about doors and things and thinking about doing this. And Andy comes along and says, well, what you need is an efficient protocol to be able to send this data around. We discussed the whole issue of separating data and control and thinking about safety critical systems and so on. So he introduced us to the idea of MQTT.
Today we welcome Professor Jeremy Graham Frey, Professor of Physical Chemistry at the University of Southampton, public university southwest of London. As far back as 2006, his laboratory was using MQTT and Java-based mobile applications to monitor critical systems related to lasers and other equipment necessary for his students to perform their research effectively and safely. This episode is a deep dive into the synergy between human ingenuity and machine efficiency, offering valuable takeaways for technologists, researchers, and anyone interested in the future of scientific exploration. This is our first episode of this podcast, and I think that's a really interesting coincidence with the fact that you were really the first documented use case of MQTT that I could find when I was, really rummaging through the Internet Archive to figure out who was there at the beginning. And of course, having talked to Andy and Arlen, I know there was some work going on at some of the oil companies and things like that. But you were really public about it. So I'm kind of wondering, if you were to take yourself all the way back to the very early days of that, what even led to you using MQTT? What happened?
I think this is taking us back to the early 2000s, way back there. And we were very lucky that clients had, literally just by accident, actually, that the UK research councils were going to fund an effort, or what it came called in the UK eScience. It's called cyber science in the US and various other names around the world. But it was basically to fund the program in using computers to aid research. Now, some of that was big computation, and there was a lot that went on that. And some was all the other things that went with how can we actually use modern computation, use modern programming, use information systems to make sure that we can do research more efficiently and more productively and extend the range of research. And we bid in to do this in terms of a grant that was actually called CombiChem. It was sort of a combination of combinatorial chemistry that was around at the time, high throughput chemistry, and all the necessary data computational infrastructures that were needed to deal with this. To be honest, we weren't expected to be one of the routes that would get funded, but in the end, we were one of the few people proposing to engage with what you might call the end users. The majority of the program was really like middleware. In fact, the success of the program is that nobody remembers it because it's all gone into the middleware. It's all there. It's all being used, a lot of it. But we've got involved at the more user end. And that user end, I mean, we did look at how you ran experiments, how you could automate experiments, how you could design experiments, the sort of software needs to design them, how you could collect the data. Electronic laboratory notebooks, we were one of the early groups looking at from a research perspective, but no, there've been other studies on that. How you would ensure that the data has got quality metadata associated in it, improve reproducibility, reduce uncertainty, all the topics that actually for the last 20 years continue to be discussed. So you might think they don't help you to get anywhere, but hopefully we did. But as a result of that, we linked up as part of that project level. We were working with our X-ray crystallographers. There's still one branch of chemistry that is ahead in terms of reproducibility and data standards. I'm also committed, was a parent and still in IUPAC, the International Union of Pure and Applied Chemistry, and that's where many of the chemistry international standards are kind of agreed and set. So I come from that perspective too. And had been working with some computer scientists in Southampton who were experts in the semantic web. These were the very early days of the semantic web, relatively early days of the web when you consider what we used to do then compared to what we can do now. And we set up the various interactions, and the program that was set up, which we were then part, facilitated linking with industry. And linking with industry, one of our local industry is IBM Pursley. And so we were put in touch with a number of players there who were very interested in working with us, experts on image processing, experts on databases, experts, as it turned out, on communication protocols. And that's where we met great Andy Southard-Clarke, who was a great, as you will appreciate, tinkerer with things as well as a master inventor. And when we were talking about, what do you do now? You do experiments. What do we want to do? We want to make sure we do experiments properly. Probably is, you design them well, and you look at the results at the end, and you work out, what worked, what didn't work, what can we improve? How are the results of one day different from results of another day? Now that means keeping a good record, but it also means keeping a good record of all the things that are happening that at that point that you might expect to influence the experiment. It's always a circular process here because you learn more as you're doing it. And I was working at the time on experiments that looked at chemistry at the air-water interface. And we used to bounce slides. I won't go into the details at this stage of the experiments, but we had a relatively high power nanospectral lasers, which were reasonably state-of-the-art at the time. And imagine if you've got a dish with liquid in it, then it bounces around and people jump around in the rooms. Now people open the doors, close the doors, making sure that people didn't walk in unexpectedly finding a laser on, which is dangerous. Are they wearing the right equipment? Recording the temperatures. I mean, we actually had some new labs built at the time, into an old building. And you would have thought we might have had access to the building management system to know the temperature of the room. No, that's not allowed. That's not possible. So we are stringing sensors around about doors and things and thinking about doing this. And Andy comes along and says, what you need is an efficient protocol to send this data around. We discussed the whole issue of separating data and control and thinking about some safety critical systems and so on. So he introduced us to the idea of MQTT, that we could have a system there. We could collect up the sensors, data, modify it as needed to digitize it, send it around, record it, send it off to places to keep it, query it, and so on. Also nicely, he introduced the idea that IBM conveniently ran a publicly accessible broker, not something that we could do directly from the university because of security issues. So we could send out data to it and receive that on mobile phones. Mobile phones did not look like an Apple smartphone in those days. I got some pictures with traffic lights and things on them. And we did, in the end, end up in the media with us sitting in the bar, which is well known, apparently, chemists spent all the time in the bar, monitoring our experiments. So it was really this idea that one of the biggest questions you always have when you're doing experiments is, have you recorded all the conditions that are going to govern the experiment? Have you controlled for all the conditions you need to? This often only becomes apparent as things go on. One of these, for example, when we failed, is that we sometimes used a Teflon dish and sometimes a glass dish for very good reasons. But we didn't always, it seems, record which one was in use. So had we put a camera above this particular piece of book, we might well have got more information. But cameras were not so simple to obtain in those days, and the bandwidth of sending images around was not as good as now. Now we do have videos and things running. But basically, and you introduced us this was the old days of things written in Perl and bits of PHP. Fortunately, I had some students who were very keen on working how to do that. They broke the software was there available. This was the very early days of the brokers. At that point, MQTT was not a publicly available standard, but we had agreements with IBM that we could use it. So that's how we got going. And we wonderfully could send control signals out to move the stepper motors on, change the start and stop the laser. Well, start and stop the laser onto the experiment. We did not have the control of the laser under the control of the computer. That was on relays and things. If you opened the door, it went off. But we recorded the fact that happened. So data was flying around, filling up our databases and so on. But it did ultimately mean that we could look back at all the data recorded and the parallel environmental conditions, what was going on. And there was one amusing time when all but one of the group we were all over in Paris for a meeting, and we were talking about what we were doing in these labs to make them smarter, make it easier for the students to work with. And importantly, when I asked them questions about what they had been doing, they could refer back and get the information easily. But we displayed this, and there's something going on. The temperature in the room is changing. Now, these are temperature rooms that were somewhat air conditioned because lasers like to be constant temperature. So we sent a message back again. Not so simple in those days. You couldn't just send a message back, but we got a message back to the last student who was there doing some work saying, can you go down and check what's going on? Because we think the air conditioning stopped. And of course it had. So she went back, turned it back on again, reset everything up, and lost much less time than she might have done had we not been able to remotely monitor it, right? I'm sure she would have picked it up as a bit later, but we could look at that whole situation. So it kind of proved a point. And yeah, we went on from there.
Awesome. Yeah, I mean, I think a lot of listeners might be, or viewers might be imagining like this was a turnkey solution even back in 2001. I'm imagining that it wasn't. I think you're very humbly sort of outlining the work that you and your students did to wire this stuff all up. I mean, can you go a little bit into the technology of that? Like, there really wasn't even any TCP/IP pieces then, I don't believe.
No,
so how did you make this
no.
happen?
You're absolutely right. This was not far from turnkey. And in fact, in many ways, the system has been reproduced several times over the last 20 years because things move on and do get easier. The way that, yes, there was no plug and play type thing. No sensors that themselves communicated even on USB, let alone on an internet protocol. Yeah, we were busily putting in Hall effect sensors on the doors. We were wiring up various thermometer type systems. I mean, at least there were ones you could generally buy something that would give you a voltage back already. So we would then plug that back to some ATD converter. These days, that's now like a Raspberry Pi. Those days, it was coming back to some big box of National Instruments, ATD converters, and so on. Wiring all those things up, putting light sensors in different places, and again, essentially running those to ATD converters and picking up those voltages. We also, the actual experimental data was also thrown through these systems. In that sense, we were fortunate the experiments ran at about 20 hertz. So there would be a short flash of light, 20 times a second, and then we would have detectors picking those up, those very weak signals. And the boxes that were these box burn detectors integrate over time, and then a little bit after the laser was gone, they would put a stable voltage out at the back of it, and we would then read that with an ATE converter. So we would be polling them at the appropriate time, making sure it was well enough after. So essentially, you would read when the gate pulse of these time window had finished and convert was done. You could then read them. So it was all bespoke wired up. So we had lots of cables going around the room, lots of long BNC cables, picking up all these voltages, bringing them back to an ATD converter. Now, the next stage when we moved from that and did it again, we then did have many more systems that would at least put them on. You can put a small Arduino or something right there and send back at least a digital signal. Now, then we moved on again. to something with USB pluggable, so you can have these sensors that everything was already in the sensor, and you would get the USB signal. And even these days, it's now out on Wi-Fi.
Yeah.
And you pick it up. One of the interesting things that we were always worried about is that if we're all wired all up, and you know exactly, well, you hope you label everything, know where the cables are. But all the cables, because as the safety reasons, we can't have cables all the way on the floor. So they would go up into some ducting and back. So if you didn't label them, you were in a severe problem of checking each time with the multimeter, which cable was which. After that, we labeled. But it was knowing which sensor. And they do swap some sensors around, then there's always a worry. The best things that we have now are the sensors that output some code. So you do know what that sensor is, and you record that along with the message. And then, because we do find that students have a habit of moving the thermometers around, for good reason sometimes. And so what temperature are you recording? And that can mess up your metadata catalog if people move it but don't update the catalog.
I don't know that challenge has changed, honestly. I mean, I think if you look at, there's a big debate right now in the industrial IoT side around like naming conventions, when they should be applied, semantics and things like that. And I think there's sort of two schools of thought. One is to do it as early as possible so that the information being carried on these networks is as valuable to humans as it can be. Most of us don't read binary or hexadecimal or whatever is flying around. But then there's another school of thought that says, like, transmit all of this information in its raw form, whether that's, just the output on the serial bus or it's some other, encoding of the information. And that should be the information. It's like that sort of like level 0 information. And then, for additional use cases or for additional, solutions, those translations, those metadata application semantics can be applied later. I mean, the world I'm familiar with, building controls, automation and controls, like for example, Modbus is a very popular protocol. It does not send anything that's even remotely human readable, really, in its most modern version, but it does send, with every single sort of reading or every packet it sends, a host ID, a controller ID, a network ID, etc. So if I think back to what we were doing, in the same time period, like 2002 or 2005 in buildings, we were getting that to a system which we could, as quickly as possible, rename it into something that was human valuable. And we would sort of abstract away or obfuscate that original really important information about what it was and where it was, and we would lose and we would make mistakes, right, in the translation from that very machine speak to the human speak. Humans would make mistakes and poorly name things or make spelling mistakes and stuff like that. Is that something you guys worked with or with as well?
It's actually interesting. If possible, we keep the raw data, we keep the raw information, and then keep the translated information on top of that. So as you build up the stack, yes, make it human interpretable when you can. We tend not to have too much tolerance in the sense with the volumes of data. So in that sense, we're not in this position where if you made it all human readable, you would have terabytes. But you don't need to. So we understand that as a serious problem and sometimes necessary to the binary. But we would tend to keep the raw data with us. Now, originally, that was the process. We might keep the raw voltage and then the conversion of that into a temperature. Once we have more standardized sensors, we tend no need to get back a temperature that's been calibrated. But at least we know where it came from, so we know what calibration it was using. So we can try and maintain that pathway. Now, that can lead to a cascade of large amounts of data. So we might be sampling the temperature of the room once a second or once a minute, and that temperature and whether it's got moved over to material lab, and we have ultra-fast lasers. These are femtosecond courses of laser. They're very, very sensitive to conditions. So we would have temperature monitors on the table, on the laser, in various places. That's really quite a lot of data. And we have occasionally run into trouble of when we didn't compress it, or actually just overflowing a disk somewhere. You can question whether day-to-day that's useful, but after a year, does it matter anymore? And I think this is where it's very important to understand that in this issue of trapping the data back to source and so on, which is very important to give that validity, to enable things to be checked. There comes a point where this is no longer, it's not a passive process that you just collect and store. It's curation of the data. So curators are people who are actively involved in dealing with the data. So you have to look. And if after a year you're thinking, well, I actually don't need that raw data temperature anymore, because I'm really not going to do anything with it. But what I can give is the picture, and we typically presented this as a calendar with the temperature profiles on them every day in a small image. Big enough to read. So you might think, well, actually, all I need to do is keep that picture. Don't really need the data behind every point on that graphic. Other ones are different. It's maybe more valuable data, and it's not a trend we need, it's the data rotation. So you have to make value judgments all the time. And I think if you don't enter into that process, you will end up with too much of the wrong sort of data being collected. But you have to look carefully and decide, is this something you need to keep? Is this something that could be redone? Is a summary enough at this stage? And that's just, there's no general answer to that. And that has to be looked at very specifically each time.
Yeah, it reminds me of something I've worked with a couple of colleagues in the past around, transmitting audio, right? So, if I think, Fourier transforms and fast Fourier transforms are like a really popular way to sort of encapsulate, the frequency, time domain, whatever. And so like when you take that and you convert it into a picture, it becomes quite descriptive and like it's got almost all of the information in there. So what we were sort of exploring, we never really got through all the way to the end, but it'd be something I would love to pick up at some point, is like, could you sort of reverse engineer the image of the FFT and get enough data out of it so that it would actually be like representative of the actual data? Like, could you do the image, could you do the color analysis and the both sort of axes to say like, okay, I can recreate this sound or whatever it is from this picture. And in that case, you have all of the technology that's been designed to move pictures effectively over the last 25 years as well, right? I mean, you've got like the best compression that's ever been, the fastest transmission, optimization, all of that. Like, are you guys moving pictures around? And
we do. I mean, increasingly, and the more modern experiments that we're doing, we're actually doing imaging experiments. So the experiment is on fast phases. It actually makes an extra match. So we are intrinsically creating images. In fact, it's worse than that. We record. It's a classic problem with X-rays. You do not record. There are no lenses in the X-ray picture. So we have this problem that you can't image in quite the same way. So what we record technically is the intensity of a diffraction pattern. And we have to use a very significant amount of computation that we can do in this case because we have coherent laser generated systems to get the image. But there we are definitely dealing with images. Now, and we definitely keep those images and we keep the data behind it. The issue of reconstructing something from one form to another, actually, we do quite a lot of this, but because we have to, not because we should. In the sense that if we do create the picture, well then, yes, these days you can very easily sweep over the picture and get the general trend. But if we really thought that we ever wanted to reconstruct the actual temperatures in detail, then I would say, no, we shouldn't cut the temperatures. If there's a use case for that, we would keep it. Now, what we also, as a completely different line that we're doing, but did come out of the whole ESAS program, is the problem of we don't, as I said, ideally in an experiment, you record exactly why you did something, what you did, and the results you got. Now, historically, we do this in a graphy notebook. Those that become somewhat digitized, digital research notebooks and graphy notebooks. And that was part of our original project, which is we kind of had an agreement with colleagues who were interested in analyzing prior information. But we would look at fixing the future so that their job would become redundant. There was no need to read the text anymore. Try and pull out of the human readable story what the data was. And that's worked on. Actually, the difficulty of getting stuff off the page, especially if it's handwritten in the notebooks, turned out to be much more difficult to solve. And it solved none of the problems about how you would characterize that and basically satisfy it. So in fact, a few years ago, because we were trying to do some modeling, we keep asking the people who wanted modeling for what data did they have, and they never had enough, of course. But a lot of the data they did have is in handwritten notebooks. So we actually have a spin-out company, Data Revival, that specializes in taking those pages, scanning them, often they're already scanned, and extracting out the chemistry from them, along with the figures and the tables and so on. Again, it all depends what you want to take out of it, depends on what questions you want to ask. We can do that, but really and truly, it's a crime because these days, I mean, when you wrote in notebooks, that was the way you wrote. And, it's really quite clever we can do that. And if people do things like use a different color pen from the lines in the page, it helps. These days, where a lot of the data is born digital, and a lot of the planning has been done digitally, it's if you think you are going to want to keep that data, and sometimes for legal reasons, for example, in the UK, we have to adhere to legislation about the type of chemicals that we use and make sure they're safe. And you keep that planning and information and potential exposures for 20 or 30 years. So we have to have that, and it should be in a form that we can flatter what's in it. But if this stuff is born digital, it's better to keep the digital copy. It's always one of these things for years when we're always doing it. That's a nice graph. I have to print it out and measure it up. Now, these days, it's a little easier than that, and to do other things, I can get the points back. But really, we should have published the data table with it. Yeah. Now, again, there are limitations. If you have to run an experiment in CERN and you have terabytes of data, not that simple to publish that data. So again, this is nuance. But in many cases, the critical stuff that might want to be reused would not take so much space to publish. And then you have the data, and you're not introducing other steps. But we can do all of that. Now, part of what meant to our labs and our MQTT is we have equipment of different ages, and some of the equipment I can put out is to put it on a dial, and we have a reading, and it doesn't have a digital output. Well, no problem. We've got a camera in front of it, and these days it's remarkably easy from that picture, even in a video stream, to extract the number that the dial is pointing at, and then output the number. So you don't need to replace what was really quite an expensive and sensitive instrument just because it's hard to digitize it. Oh, put the camera on it. Let's some quite amusing things actually. We have a vacuum chamber, big piece of metal, and you want to monitor the pressure. So you have a pressure gauge on there, and you have a dial. So it reads off it. That actually could be digitized. So we have a digital, we have a recording of what the pressure is. We had some interaction with some colleagues in another university who were good at building 3D models, virtual models. And they built for a while a virtual model of our lab. It was kind of, you could imagine it being built in a Minecraft style world. Yep. And in fact, there are MQT feeds into Minecraft. And they had a module into this sort of system that meant that it could read the data stream coming off the MQTT pulse-up feed. So it subscribed to the broker, and it took the pressure off the chamber and put that on the 3D model. The interesting thing is, where would you put it? So they put it in the middle of the chamber where you could see it. But of course, in the lab, you don't look at the chamber to see the pressure, you look at the dial. But really and truly, especially if you're doing this remotely, you look at it's in the chamber, that's that chamber. So this changes the whole user interaction and feel.
It does. If I think back to my days in plant operation, like, I think these ideas, we explored them. I'm sort of wondering though, like, would there be some aspect to like truly remote monitoring like that where something could be missed? Like, for example, like we had input and output pressure gauges on all of our pumps. If we could digitally monitor them, we could just scan, like you said, a graphic and see that everything's okay or everything's about to explode. But I wonder if you would miss, like, I would walk through that pump room and you would hear like little noises where you'd be like, wait a second, you'd be hearing the early precursors of bearing wear, or you'd see a leak, a drip, somewhere, and you'd be like, oh, we need to address that. I mean, you can't go into
actually,
obviously.
We've looked at that analogy. So what we find is that I found that I, as a supervisor, not in the lab say all the time. So it don't have to be kind. I might walk in, talk to the students, and that doesn't sound right. They've been there all day. They're not going to pick that up. And it's like if you take your car into the garage before the electric ones anyway, you just turn it on, and the good guy says, "Oh, yeah, I can hear that very well." So what we are doing, we tried a few tests, and we haven't quite limited yet. We've been meaning to for several years. Is we put microphones on the pumps, and we actually record the Fourier transform of that and watch it, and then of course the system can alert you there's a new frequency there, or something is the balance has changed because as they were. What I'd really like to do is to set this up properly, to actually get everybody to contribute. I want to crowdsource this, so that when people's pumps make strange noises and then they do discover what the problem was of the pump, that you can look it up. So, oh, not this pump, it's making this kind of noise. What does it mean? Which bearing do I need to change? And I think we could all crowdsource it. It may be even the instrument, the people who make the pumps. They, of course, have aged and worn their pumps to test them out. Accelerated wear test. So they might contribute the data because, of course, we can buy their spares. But the idea of preventive maintenance here. We monitor the current and voltage. It was another thing that Andy Stavros introduced to us because he was a separate project, was doing some of these early stages of these meters that actually monitor the current and voltage, actually recording your consumption. Interesting early stage problems because of the mix. You are not allowed in the UK to mix high voltage connections. Let's go 240 volts. So the sensors were a bit clunky, and that's a problem. That's got a lot easier now. But we can watch the current consumption of the pumps or the recirculating coolers and so on. And if that started to rise, again, you knew that there was wear going on. So these things became very useful. And they're putting more and more of these sensors in. So certainly in the next lab that we're allowed to build, we will have these vibration monitors on things. Turns out smartphones are not great for doing this because they're good for talking, so they filter out all the rumble and stuff. I believe on some of them you can get the raw audio feed and stuff, and of course it will do the Fourier transform on the phone. So that is the next possibility. You just hold the phone up and scan it around and get. But yeah, that is definitely the plan. That there are lots of things that you see in here. And actually knowing that, we can put the relevant sensors in. The grid has more of a problem, but monitoring fluid levels in places is a good indication. Although our general experience of mine over 40 years of working with some of these stats is the flow sensors tend to break before the flow is actually a problem.
Yes, I've also experienced that. Not to mention like all the complexities of spanning and things like that. 4 to 20 million conversions or whatever. Those were. I remember those days fondly, but I'm also thankful that there's better technology than what I had to deal with back then. So that kind of leads me maybe to like more philosophical side of questions is, I mean, you've obviously done amazing things to like digitally transform the lab for both the benefit of the experiments and the science, but also the students. And I think you have like this probably unique perspective of before times and after times in terms of this type of work, this type of research, and the purely analog, hands in the wet versus, the more modern, this like what you're building for your new lab. And I'm wondering like what the pros and cons you've sort of seen are there. Like, I mean, technology isn't always good forever. Even as technologists or futurists, we can't really make that claim. So like, what could we do better? What, do you wish we could turn back the clock on? What's the sort of gut for you there?
So no, I would not wish to turn back the clock. I think the curriculum I used to, we have certainly removed some of the tedious things, some of the unreliability things that make it is very difficult for to students to do and get the reproducible results. So I wouldn't wish to turn back the clock, but I think we do, like every age that has it's the same thing. Black boxes can be a problem. So, do you have a black box that the whole sealed it becomes okay, it does what it says it's going to do. But if you don't understand what it's doing, then you can run into trouble because you don't know. So, what we're doing? I mean, simple things like knowing the knowledge that you can overload a sensor and saturate it. If you don't know that, you don't realize that the output that it's giving, which you just see as a set of numbers, may not be of true and accurate portrayal of what's going in. So I think the important thing is great that those things exist, and certainly wouldn't require all students to build them from scratch. That's crazy. I regret sometimes how we have to keep moving on the technology because you can't buy the replacement parts of the old ones. The students have to know enough and be educated enough to understand what the measurements are and what's going on inside these boxes. Or if you can't fully understand it, to be able to do enough measurements on enough conditions to understand when it's reliable. And that's quite difficult if you are not really sure what the processes that are going on inside some of these transformations. But the ability to record more things without tediously having to write them down all the time and making mistakes there means that it's a lot easier for the students to process that information. I think the exciting thing is coming along now is that you may not even have to write your program. I think all scientists basically now need to be able to write programs. They're going to have to use software. It's better that they also write some. But again, they should have some basic software engineering training so that when they write some programs, other people will use their code. But they're not going to be software engineers. Other people will make Rust code and so on. But they're going to try things out. But it does mean that they can process more data and get insight from it. But they still need to, you've got to look at it. You've got to plot it in different ways and look at the data. But again, the abilities of things like some of the large language models to help you with that, if you set up the context correctly, and to do some of what we might do the heavy lifting. Assume that we've done a good job about collecting the data and it's got the right metadata on it. So we do have at least the units. You will discover half of your measurements are in one unit and half of them are in a different unit. It might be Celsius versus Kelvin, or it might be centimeters versus inches. Right, okay. It's got intent there. You know what you've got. You know what you're doing. Your data is at least fair and is findable, interoperable, addressable, and reusable. But rather than having to write a program to tediously go through and make that conversion, you can now load that into one of these systems and instruct it to do it. So what you could do with, tens of points, you could now do with thousands of points and know that it will probably done it reliably. But understanding that you have to check for that and may have to do a bit of work because it's all in one column, it's not conveniently separated, and actually you don't know whether somebody's put an uncertainty there as well as a range, which is not the same thing, as well as the units, and doing a bit of work to do that. That you have to know you're going to do and know why you're going to do it, and that's what the professionalism around being a scientist is doing. But you've got tools to help you do this. And you don't have to say, well, I'm only going to be able to do one experiment here because I just don't have the time to do all of this other stuff. Now it becomes possible to do all of that. So you can do the proper thing. Right?
So it's like kind of finding that fine line of precision, right? And saying like, okay, like if we can, this precision in calculation, this precision in communication or whatever is sufficient to advance the science.
Yes.
And as long as we can keep all of these modern tools on the right side of that line, right? Like, I think people oftentimes are looking at these LLMs and saying, well, they hallucinate. And it's like, okay, well, if you consider hallucination, it just making something up or making a bad assumption or putting together some words that it once heard in a conversation that it just thinks logically goes together. My belief is that humans do that all the time.
Well, exactly. Yes.
Yeah. So like, it's kind of just making sure that our machines on the data interpretation side and the data processing side are equally or more precise than are the data systems on the communication side, right? Because it's,
Yes, it's important though that right from the start that we put the right information in the raw data, if you like, so the data with it. Otherwise, you have a problem from the beginning. Really important to make sure that bit is right and feeding forward. There is a problem. I would say the problem with some of these model systems is not the hallucination. As you said, friends and colleagues do the same thing. And out of some of those hallucinations comes some of the best ideas.
That's right.
But what I think is people are experimenting with once they see is that these systems are non-deterministic. So if you ask the same question more than once, you don't get the same answer, which is again just like dealing with people. So you've got to be aware of that. And it's just the same thing. We do experiments more than once and we don't get quite the same answer. And the big thing is, okay, that's fine, but why? And understanding the why is often then the root of actually understanding what the problem you're investigating is. What is affecting all of these? Does the situation affects that? So one has to be careful, which means one has to have some reasonably good knowledge about what it is that you might expect to happen. So you've got to have a good fundamental training in the area that you're working on. So if you've got that good basic fundamental knowledge, then you're going to be able to look at the results and say, that looks strange. Now, that could be because something's gone wrong, or it could be you've discovered something that's going to give you a Nobel Prize. But either way, you need to recognize that. And I think in terms of discovery and doing new things, my colleagues who are the really cleverest are the ones who choose the right experiments to do. And the next set of clever people are the ones who recognize the interesting result when they get it and pursue it and choose the right one. And all I talk about here is trying to help one do reliable experiments so that you can spend more time doing the clever things and thinking about stuff and being able to trust, well, this is what this experiment gave. Therefore, what does it mean? As opposed to always thinking, well, how do I control for this, that, and the other? You will know what you control for, and then, so we have control for this.
Yep.
And then put sensors in to deal with that or control it.
Do you think the nature of what you're describing in this doesn't look right, or this doesn't feel right, or this doesn't make sense? I think a lot of people would describe that as intuition. And I think that like intuition is a uniquely human sort of, process. Do you think that the machines, the artificial intelligence will ever get there in terms of being able to tell you, not from a purely quantitative perspective, but also from a qualitative perspective, that something doesn't look or feel right?
Well, I don't know, because I'm not sure how much of that intuition. I mean, we've got intuition and does things and so on. But it comes from experience. It comes from seeing what things look like, but it also comes from some basic concepts. So in chemistry, because the laws of the thermodynamics are not going to be violated by an experiment I do. So if more energy comes out, then I think there is a problem. If things don't balance in terms of mass, something's gone wrong somewhere.
I would say Lawrence Livermore would like to have a word on that one.
No, but they put huge amounts of energy into them. But they know where that extra energy is coming from, and they know what's going on. So I think a lot of this is based on really fundamental chemistry, that physics that we know. And so we have, with experience, have brought those rules in. We understand. We've also done calculations and made mistakes ourselves. You look at an equation, and you're looking for the symmetry of the equation. And there must be certain symmetry, because physically it doesn't matter if you swap some things around. And if your equation doesn't have that, probably means you've made a mistake somewhere, unless something very significant has been built in there, which can. So anything the answer is those ones that are based on fundamental basic properties of science. Those ones, yes. We may have to call the large language model's attention to them. Actually saying, you said this, is this consistent with this law? And at that point, it may or may not be able to do something. The creativity angle, thinking of something that has not been done before, that isn't something you would look up, that is using an abstraction to relate things that is not part of the canon, that's going to be very hard. And that's where certainly people do that. And you ask the people, that's where I say, the people who choose the right experiment to do are the cleverest, because they've chosen to look at something because their creativity has suggested this may break the rules and give me the information I want. I think, though, we can get close to it in areas where you're looking for a new drug, but you're looking not for a completely new family of chemistry. You'd like to sometimes, but then when you bring those chemical models in, you can run some experiments, and then you can look at that data and say, where is building a model? Where is the maximum uncertainty in my model? What molecule could the generative AI suggest you make, based on all the other molecules around, that will minimize that uncertainty? And it will make some suggestions, and you'll look at them and say, I can't make half of those. Well, actually, it's not probably anymore, because the system can tell you which ones can be made or which ones you can buy. That's getting better and better. So those things, but that's still usually within the remit of chemistry you've already taught. So that's why I think there are regions of creativity that are going to be very hard to reach in these AI systems. And the ability to craft, as we've often said, I'm sure you were probably taught it at school, asking the right question is actually one of the most important things you can do. And that's exactly the same with these large language models. Setting the context up and asking the right question will get you the right useful information out. That is no different.
That's profound. Yeah, I mean, and I think like my big takeaway from this conversation, again, thank you so much for taking the time to talk with me and outline this for everybody watching and listening, is that like what you've really done through 20 plus years in your lab is you've like you've kind of made like a superhuman researcher, in that like you've you've expanded the ability to sense, right, through all the sensors and the communication and all the stuff that MQTT has enabled. You've sort of enhanced the ability to recall or remember, because like you said, you're digitizing all of these existing handwritten records. You're probably historizing a lot of the data that comes across, like you said, in its raw format. And it sounds to me like potentially the next area that you'll be investigating is in not replacing the human's ability to sort of interpret or expound on, but to actually like enhance their ability to do that with these new technologies like AI. So is for you like the lab of the future, the sensors, the communication networks, the data storage, the ability to keep that data in a format that will support today's and any and all future questions, right? And then to help with all of these new technologies, the people who need to really bring the creative to the process to support them in terms of like the questions they should be asking and things like that. Because I mean, and we can close on that, because I think if that's what you're doing, that's amazing.
That's certainly true. What it also allows them to concentrate on is what experiment are you doing? So, what do you want to measure? And how are you going to construct a system to enable you to measure that? Once you've decided that, all these systems can kick in, all these tools will help you make those measurements, record the measurements, get quality, uncertainty estimates, help you with tools, analyze it, and so on. But the creativity has got to be, I've got a laser. What am I doing with that laser measurement? Why don't I use the laser in the first place? Can I build a better one? To make a better measurement? What molecule do I put in there? What interaction am I trying to speak? We help the students and the researchers be more creative, think of new experiments, be able to do those experiments, and then be able to work out why they are or are not working, and extract quality information, reliable information, learn something from it more easily and efficiently than they have in the past.
Wow. Well, I'm glad you're doing that. This gives me a lot of hope for the future of chemistry and the future of research, and of course the students who are lucky enough to come through your lab. So thank you so much again for taking the time. This has been awesome. We'll definitely keep in touch. And as you know, we're looking at when we come back to do our 50-year celebration of MQTT, we'll be sure to check in with you and find out what's going on there over at your labs.
Absolutely.
Thanks again.
Thank you very much. This was a great pleasure.
Me too.